So in this section, we are going to look at the electric motor system reliability. A system is said to be reliable when it can deliver what it is intended to deliver. That is, it can function as at when it is needed, as it is intended for it to function. Such a system is said to be reliable. Okay, it's just like the reliability ordinarily that you know. Somebody is reliable when he could deliver on his promises or what is expected of him. So it is too with our assets. Okay, an asset is reliable when it can deliver what it is installed for or designed for to deliver, and it will be able to deliver that designed or expected capacity as at when it is actually needed of it to deliver. So in the case of our electric motor system, it can deliver on the reason why it was installed in the first place, when it is actually needed for it to deliver on that particular reason. So in that case, we can say the electric motor system is reliable. Okay, that is the ability to deliver as at when it is needed. Okay, what it is expected of it to deliver. Okay, so that is the reliability of the electric motor system. But as we will see later, there are various components in this electric motor system. So one of the mistakes that we often do in asset management is that we look at these components in isolation. Okay, we try to improve the reliability of each of these components in isolation, and doing that means that we fail to realize that these components, they are in series, which means that the reliability of any of the components in that series will affect the reliability of the entire system. How do I mean when I say the reliability of a component? So if you look at the right of your screen now, you will see the electric motor system ranging from the power input, okay, input into the system, to the feeders, to your electric motor, the circuit breakers in line with your electric motors, the contactor, and also the control circuitry, and of course the electric motor itself. So you will see that the reliability of all of these components, including the cabling, the feeder lines, okay, the reliability of all of these components, the electric motor, the feeder lines, the contactor, and the circuit breaker, and if you have isolator switches on them, all of these, and the control circuitry, all of this will affect the reliability of the entire system. So when you are looking at improving the reliability of the electric motor system, you have to look at it holistically, okay, with a view to improving the reliability of each of these components in the system, and as such improve the reliability of the entire system. And if you also look at it, also to be included is the load that will be driven by the electric motor, as you can see on the right of your screen, on the left of your screen, I mean to say. If you look at this load here, which is a pump, okay, you will notice that what we actually expected in our process from the electric motor system will be delivered by the pump. So if the pump's reliability is 40, remember it's in series with the motor, which will be in series with all of these components. Okay, so the reliability of the pump itself will also affect the reliability of the entire system. Remember, reliability is the ability to deliver what is expected of the system as at when we need it to actually deliver on such expectations. Okay, so the mechanical parts, the load that is driven, if it is fan, if it is compressor, or as in this case now, if it is the pump, the reliability of the pump also affects the reliability of the system. And of course, the reliability of this coupling and the pipings, okay, all of these will affect the reliability of the system. So when we are looking at the reliability of the electric motor system, we put into consideration every component in the electric motor system. Okay, so before we go into improving the reliability of each of these components, let us first appreciate how the major component, okay, remember we termed it the electric motor system. So in this case, we are focusing on the electric motor, okay. So let us see how the electric motor functions, because the understanding of how the principle guiding the functioning of the electric motor will help us to be able to discern when issues are developing. Okay, so let us look at the basics of electric motors operation. We know that electric motors have two major component parts. Okay, it has the rotor and the stator. So each of these stator, as you can see, they have windings in them. They have three-phase winding that are wound into three-phase belts. Okay, so these three-phase belts, they are separated by 120 electrical degree. Remember, because in the course of this program, you will come to see how that affects what we are expecting. Okay, because the input power, they also have that kind of phase relationship separated by each of the phase separated by 120 electrical degrees. So that is what we see here in the electric motor. Okay, so the terminals, the lead outs from these windings, they are connected to these terminal blocks. So we have two lead outs from each of these phase belts, okay, on the terminal block. So on the terminal block, we have 6 lead outs or 6 terminals, okay, 2 from each of these phase belts. So on the terminal here, we can either start, as we have discussed in some of our other trainings, we can either start the motor or delta the motor. You can check out our earlier training on electric motor or electric motor testing, okay, or the use of digital multimeter in testing electric motor. So that is the stator. Then the rotor, as you can see, we have windings in them too. Okay, these are conducting bars, as you can see on the rotor, aluminum bars. Okay, we have several of them, as you can see, and then this bar is shorted by this end ring. Are we getting it? It's shorted by this end ring. So that is what you are seeing here now. Okay, so these are the aluminum bars, okay, and then this is the end ring, as you can see on the screen. Okay, so these are the windings. These bars, they are the windings on the rotor. Okay, so let us see how it affects the operations of the electric motor. Now remember that when you connect the electric motor to your 3-phase signal, as you can see here, it means that you are sending voltage that are displaced by 120 electrical degree from one another. That is the 3 phases into this stator winding. So that will end up magnetizing this stator winding. So that stator winding, the magnetic field that will be created will be rotating in the direction of the rotation of that electrical the voltage signal, okay, that is coming into the electric motor system via, that is the electric motor via the terminal block. That is the sequence, Okay, if it is red, yellow, blue, it will be going in that sequence displaced by 120 electrical degree. So the field that will be generated here, okay, will also exhibit that sequence. Are we getting it? So that changing magnetic field as it's changing, because the terminal is directly connected to your line now. So as that magnetic field is changing, what will happen, since this one is coupled inside, it will now induce current. That is, current will now start to flow in these conducting bars. Remember that current carrying conductors have magnetic fields generated around them, which means magnetic field will be generated around this rotor. Okay, so that magnetic field on the rotor will now interact with the magnetic field on the stator. Okay, that is what we call the magnetic flux linkage, or linkage flux. Okay, and the resultant effect will be that tangential force will now be created on this rotor, and the rotor will start turning, okay, in the direction of that phase sequence, okay, as we have discussed before. So the electric motor will start turning. So anything that could affect the magnetic field that is created by either the stator or the rotor will definitely affect the integrity or the reliability of the electric motor itself, okay, which will in turn affect the reliability of the electric motor system.